So let's first discuss frequent pattern mining in data streams. We know in current big data era, besides we get a huge amount of data stored in database systems, in file system, on the web, but also we have Internet of Things or Internet of Sensors. So in those kind of scenarios, there are lots of stream data. The stream data, the feature usually is they come in and go continuously. They are ordered in the sequence, but they are changing dynamically. They come in and go very fast, but in very huge volume. Okay. This is very different from traditional finite persistent data sets stored in the file systems, in database management system, or on the web. So now let's look at the major characteristics of data streams. First, data streams usually represent huge volumes of continuous data. They could be potentially infinite, like the online sensors. They have no ending at this point. Okay. So they are fast changing. They may also require fast real-time response, like anomalies or emergency handling. Okay. Then for data stream, usually it captures nicely of our data processing needs of today, because even in database systems, the data could be so huge, you may only want to scan them in a sequential manner like data streams, or you don't want to keep repeating, getting them back again. Okay. So to that extent, even in the large data stored, you may also process them in the data stream manner, not to say you really have to enter large amount of sensor data. So in general, we say for processing data streams, random access is expensive because the data come and go. You don't want to fetch back, or you cannot fetch forward as well. So usually we call these algorithms developing data streams called single scan algorithm. That means for any particular data set, particular page, you can only have one look. So another interesting thing is the data stream, in many cases, you may like to store some kind of sketch, store a summary of the data seen so far, instead of storing the detailed data, because you don't have such volume or such processing power. Then another important challenge is most data streams actually are coming at a very low level, like the particular sensors, and they also come in multi-dimensional feature. For example, even for the data, they may come, some part could be the temperature, some part could be video, some part could be audio, some could be the text data. Okay. So it's multi-dimensional in nature. But for the information processing needs, usually you want to summarize or process the data and pattern at a multi-level and in multi-dimensional way. So we can see there are lots of research challenges on data stream processing. If we look at the architecture of data stream processing system, usually we call this a stream data management system. What we have is we have a stream query processor. You get a multiple data streams streaming into this processor at the same time in a continuous way. But even for user or application programs, they usually post continuous query rather than ad hoc queries. It's like a watchdogs. They want to see anything abnormal. They want to summarize the data in a multidimensional space. And then for this stream query processor, usually you have some scratch space. They could be a big main memory or even plus some disks. These multiple streams coming down here will be summarized, processed, especially answer your continuous query. The results will be streaming back to the user's application programs. So this is a typical way to process streaming data online in the real time. Okay. The problem becomes for frequent pattern mining. How can we find frequent patterns in these data streams? Actually, it's pretty challenging. Then we look at the major differences between stream mining versus stream query. Okay. The first thing is stream mining and stream querying, they share many common difficulties. For example, you can only do single scan, you need fast response, you have to handle dynamic noisy data. But for stream mining, usually you want to see the global picture, you want to see patterns, you want to find the clusters. It often requires less precision than the stream querying, because stream querying want to pinpoint to a particular point. You may need to perform join, grouping, sorting, which actually in streams, join and sorting, those algorithms actually is pretty difficult because you cannot see the past data, you cannot predict the future incoming data as well. But patterns are hidden. They are more general than querying, so their processing is different. Actually, for stream data mining, there are lots of research and development activities already. One branch actually studies pattern mining in data streams. Another is doing the multi-dimensional, multi-level online summary of data streams. And also, data stream can be clustered dynamically, can do dynamic classification, can find outliers and anomalies. So there are lots of research in data mining in all these frontiers. So what we are studying in this lecture, we will only touch pattern mining in data streams. So one important thing is for mining frequent patterns, in stream data, it is unrealistic to try to find a precise frequent patterns. Simply says the past precise thing may already be gone. It's pretty hard to capture them. The future one may not be coming yet, so it's pretty hard to predict them. And even for the one you can hold, just because they are so big, you cannot store them even in a compressed form like FP3. So what we expect is trying to find approximate answers. But in many cases, approximate answer may be sufficient for our analysis purpose. For example, you may find a router, could be interested in finding the flows, those flow in the network. You may find whose frequency at least 1% of the entire traffic stream seen so far. If you identify those patterns, those frequent occurring flows, you'll probably be pretty happy. On the other hand, you may say, if you, for this sigma, if you give me the count, it's probably a little less like over 1 over 10, or you would say the error rate is 0.1%, you probably feel it's very comfortable. You think you're doing good thing already. Okay? In that case, we may develop some very efficient algorithm to mine such patterns with good approximation like this. Okay. Then in this lecture, I'm going to only introduce one algorithm on this, which is called lossy counting algorithm, developed by Manku and Modwani in 2002. Okay. The major idea is not to keep all the items, especially not to keep the items with very low support count. That means if they're very low, they unlikely will reach the frequency threshold. You do not even keep them. Okay. The advantage is you can guarantee some error bound. That means I actually find all the frequent items. Okay. But of course, you need still to keep reasonably large set of traces. Your buffer size should be rather big. Let's look at lossy counting algorithm, but we only introduce frequent single items. Okay, they did study multiple item sets. For the simple explanation of the idea, we first look at the frequent single item counting. Okay. Suppose you get a very, very huge, data streams. You may divide the stream into buckets, but the bucket size could be 1 over epsilon, because your epsilon is 0.1% error bound. Then the bucket size could be 1 over epsilon, means 1 over 0.1% is 1,000. Means each bucket should have 1,000 items. Okay. Then this 1,000 item, we assume that the main memory size is big enough, you can easily hold this one bucket. Then at the very beginning, when the first bucket comes, the main memory at the very beginning, you can assume for this part is empty. Okay, the summary is empty. But then you get the first bucket, you get 1,000 items. Okay, then you start counting them. For example, you may count there are 4 red ones, there are 2 yellow ones, there's 1 green one, 1 blue one, black, and so on. Okay, so at the end of this bucket boundary, we will decrease all the counters by 1. You probably can see there are many, if they only appear once, like the green one, the blue one, the black one, they're all gone, because once you decrease the counter by 1, the counter is 0, they are gone. Even for red ones, you get 4, now you get the counter becomes 3. You get 2 yellow ones, the counter actually is only 1. Okay, so that means you actually count, your counter actually get less than the real one. Okay. When the next bucket of the stream coming, okay, you probably see you actually empty a lot of space because the counter was not existing. There are too few items in this color. Okay, then you may get additional red ones and yellow ones, or even black ones. Okay, so you can see at the end of this bucket, okay, then you will do the same. You decrease all the counters by 1. So those not frequent, they are gone again. So the yellow one, you can see originally you get 1, you get 1 more, but you decrease by 1, you still keep 1. The black one is 1. The red one, you get a little more because the red one is so frequent. After you're thinking bucket by bucket, you get many buckets. You still keep this counter, 1,000 counters. Okay, because you get 1,000 buckets. At most, you have 1,000 counters. You only get a number, so the space actually is quite limited. Okay, then if finally we want to output the frequent patterns, the interesting thing is whether we will be able to output all the frequent patterns if they are frequent in these data streams, but maybe we have some reduced count. Okay, so actually, suppose the support threshold is sigma, the error threshold is epsilon, and the stream length is n so far. Okay, then the output are those items with frequency count exceeding sigma minus epsilon times n. Simply says, if for any item you finally found its counter with this number or bigger, you will output as a frequent item. Okay, so the key is because at the end of each bucket, we decrease the counter by 1. Okay, so we will undercount something. So the question becomes, how much do we undercount? Okay, so if the stream length seen so far is n, the bucket size is 1 over epsilon, we can easily, determine the frequency counter error should be no more than number of buckets. Why? Because for each item, for every bucket, you decrease the count by 1. Okay, if some item come even later, at the very beginning they did not come, you did not decrease them. So to that extent, you decrease less than number of buckets. So if they come even at the very beginning, the first bucket, they stay all along the way, you will decrease the count by number of buckets. But what is the number of buckets? You pretty see, because you have seen n elements, okay, and the bucket size is 1 over epsilon, so n elements over bucket size is number of buckets, which is n over 1 over epsilon. So you get epsilon times n. That means the frequency count error at most is epsilon times n. We know epsilon is pretty small, so the error count error is not that big. Okay. Then we look at the lossy counting. They have some interesting property we call approximation guarantee. The first thing is there's no false negatives. Simply says if the item is frequent, it will be captured and output. Why? If we can see is if your item is frequent, that means your total support threshold should be sigma times n or more. Okay. Then, because we output a frequent item exceeding sigma minus epsilon times n, we know we already undercount this part at most. That means, actually, since you output all these, you will output every item whose support count is no less than sigma times n. So there's no false negatives. Okay. But there could be false positives. Where the false positive comes, just because probably sometimes they come later, like you may have one color, okay, suppose orange, they come at a very late stage. Okay. So they actually, the previous decrement by 1 actually did not touch them. So now they really have this, suppose their support is sigma minus epsilon times n. You actually output this, say this one could be a frequent item, okay? But this orange one, actually the real support is this, okay? They do not suffer the decrement, so, or only suffer 1. So then your support count, this one actually in principle is not frequent in real, but you think they are frequent, you just output as a frequent item, okay? So the false positive has this true frequency, at least of this, so that means the orange one have the true frequency of this one, you still count them as a frequent item. So you do have some false positive. But frequency count underestimate by at most epsilon times n, because we already have this. So you have some nice guarantee for, finally you have just this bucket size as your main memory. You actually can return, all the frequent items, and it may contain some false positive, may have some underestimate of your frequency count. But still, it is a nice, elegant algorithm with very limited resource you can handle data streams. Of course, after this, there are lots of studies by improving, for example, improving lossy content algorithm. One interesting study is by Metawali in 2005. They do space-saving computation of frequent and top K elements. The general philosophy is they may try to use more memory space. If you really have bigger memory, you don't have to restrict it down to 1 over epsilon as your bucket size. But we are not going to discuss this in more detail. Another interesting thing is in this lecture, we only discuss frequent one item sets. That means frequent single item, we discuss how to mine the approximate one. Actually, in Manku and Modwani paper, they also discussed frequent K item sets, how to maintain counter, how to do lossy counting. But due to limited time, we will not introduce this algorithm. You may like to read the paper by itself. Then there are also some subsequent studies on how to mine sequential patterns in data streams. It is a pretty challenging task as well. Okay. So I'm going to only introduce you 2 papers. One is Manku and Modwani's paper. Another is Metawali's paper. You may want to see, in how to mine streams in patterns in streams in a very interesting way. Thank you. Now we examine another interesting line of pattern discovery applications. Is pattern discovery for software bug mining. We use software all the time, but we also know software may contain bugs. But software usually could be quite big, quite long, and its running data could be even larger and more complex. So automatic debugging finding software bugs is a very challenging issue because often there's no clear specification or property we can rely on. We have to invest substantial human efforts to analyze data, analyze the source code, and analyze bugs. So if we can have certain automated tool to do software reliability analysis to find bugs, it will save a lot of people's effort. Okay. So for bug detection, there's one category called static bug detection. That means you check the source code, try to find bugs. Another called dynamic bug detection or testing is you run the code, you try to detect where could be the bugs. The debugging usually is you give me symptoms or failures. I try to pinpoint the bug locations in the code. If we can do good pattern mining, because the code or running sequence may contain some hidden patterns, if we can do pattern mining, we will be able to find some common patterns and some anomalies. Usually the common patterns likely are specifications or properties, but the violations or anomalies comparing to the common patterns likely are bugs. Okay. So if we can do pattern mining, we mine the patterns, it may narrow down the scope of inspection. For example, usually the code locations or predicates that happen more in the failing runs. That means every time it fails, you likely see somewhere you can see it happens more for certain predicates, or it happens more for co-locations, this kind of patterns, but it happens less in the passing runs. Likely those co-locations or predicates are suspicious bug locations. That may narrow down the scope for the bug inspection. So the typical software bug detection methods contain, there are many. One could be mining rules from source code. We may find deviant behavior. Those are bugs by statistical analysis. You may find some source code that substantially deviate from the others. Or you may mine some programming rules. For example, you first do variable value assignment, then you do the condition testing. So if you use frequent item set mining, you may be able to identify those typical program practice or rules. Or you also can mine function precedence protocols. Simply says, if you find some functions always precede some other functions, so you can use frequent subsequence mining to find such patterns. And also you may reveal neglected conditions. You based on different condition, whether it could be tested or will never touch, you use frequent item set or subgraph mining, you'll be able to find such patterns. Another interesting practice is mine rules from revision histories. You look at sequence of the program code revisions, you use frequent item set mining, you may find certain general practice or certain anomalies. Actually, we are going to focus on one interesting bug. We try to find a copy and paste bugs. So we try to mine copy-paste patterns from the source code. Then we try to find the copy-paste bugs. Okay. This one actually was one interesting piece of work published in 2004 called CP Miner by YY Zhou's group. And we are going to just show this. It's an interesting idea how to extend pattern mining to find copy and paste bugs. So copy and paste bugs is very common. For example, some statistics show there are 12% of the code in Linux file system are copy and paste code, and 19% of the code in X Windows system are also copy and paste. But a copy and paste may introduce errors. For example, the typical one called forget to change bugs. That means something like this code. Okay. If you see the first part, the upper part, the for loop, okay, this part and the down part, another for loop, these two actually, if you see many other things are just the same, but there's something changed. So you likely, this part or the second part was copy and paste from the first part and then do some changes. But the problem is when you do global change, sometimes the programmer may forget to change something like here. Okay? That means all the total in the front change to taken, but the last total at the second occurrence in the statement forget to change to taken. So this is a very common practice because of carelessness of some programmer. Okay? But how can we find this kind of bug? Actually, this bug has really happened in Linux 2.6.6. Okay. Then we will see how to automatically find such bugs. The general sequence, the general way to solve this problem, we will be detailed later, is we may build a sequence database from the source code, mining such sequential patterns. Then we may find some mismatched ID names, then the bugs as well. Okay. This one was done by YY Zhou's group. That time she was at UIC. So that's it's very interesting study using pattern mining. So we first see how to build sequence database from source code. Okay. So the general philosophy is for each statement, we may match the statement into a number. But how we can match the number, for example, this two are 16, the other two are also 16, how we can find such similar sequences. Okay. So the methodology is we tokenize each component. Like, just give you an example, like old is assigned to 3, and the variable new is also assigned to 3. How we can, we basically, for different operators, constants, or keywords, we may map into different tokens, but for same type of IDs, we map to the same token. For example, old and new are both same type of ID. These are both old, new. We do not care they are different IDs. We just map them into the same token 5. But it's assigned to these two map to 61. Then the value like 3, we map into another value like another token like 20. Then these two statements, if we take the same sequence, we give them a hash value. These two statements should have the same hash value. Simply say these are very similar statements. Okay. So if we do this, you can easily see this total and this total I dot address and the other one's total I dot bytes. They essentially map to the same thing. They got the same sequence. Okay. So then a program is mapped to a long sequence. We can further cut the long sequence by blocks. For example, we can find these fragments of the program is matched to a sequence in the same block. You probably can see these as a map into sequence database. Then we can do sequential pattern mining to detect forget to change bugs. How to do sequential pattern mining? Remember the previous sequential pattern mining allow arbitrary number of gaps in the middle. This is derived from the customer shopping sequences. But for programming, for finding sequence in the copy and paste bugs, you don't want to have exact one because you allow people to insert some programming statements right in the middle. You count these are the same kind of sequences, but you don't want them to insert too many statements in the middle because they could be completely different things. So we can constrain the maximum gap, like a small number of statements in the middle. Then we will still say these two sequences of the code are the same sequential pattern. Okay. Then we can compose larger copy and paste segments because they have many things in common. We can combine the neighbor copy and paste segments repeatedly. Then we may try to find conflicts. essentially we try to identify those names that cannot be mapped to the corresponding ones. For example, if you see here, you may see the concrete identifier F mapped to F1, this F also mapped to F1, but the other one is F is mapped to F2, so there's a conflict. So we try to calculate the ratio. Suppose if we find 1 out of 4 total is unchanged, so the unchanged ratio is only 0.25. If you set up an unchanged ratio, if it's greater than 0, it means something did change, but unchanged ratio is less than a specified threshold, then we can say this likely could be a copy and paste bug. Okay. So this one actually was done by YY Zhou's group. They work out a CP miner. They mine the common source code like Linux, Apache, Postgres. So they actually get to find many copy and paste bugs out of millions of lines of code. And you can see this sequential pattern mining is very efficient. That means within a short time, you can browse through millions lines of code, finding such copy and paste bugs. And based on their human identification, these are the real bugs. So it's very interesting to see this pattern mining can help finding software bugs. In this session, I'm going to introduce you another interesting applications of pattern discovery called pattern discovery for image analysis. We know image analysis or computer vision, there have been lots of techniques developed in this field. Okay. Then there's one interesting recent line of work is using visual pattern discovery to do image analysis. We can take this picture as an example. For this image, we may find there are many interest points. These interest points we call visual primitives. Every visual primitive can be described by a set of visual features, or you can think it's a high dimension feature vector. And then each image is a collection of visual primitives. Then we'll study how to turn those visual primitives into patterns and how to do pattern mining on large number of images. So that means we want to study visual pattern discovery problem. Okay. For visual pattern discovery, we can think about from these images, we can use feature extraction. We can extract lots of high dimension features. They form visual primitives. Those visual primitives can be clustered based on their space. They may cluster into visual items. Okay. Those visual items, if they are similar, then they belong to the same item. You can map them into different item ID. For example, you can map this feature into W, and maybe another picture have a similar one. They actually also call it W. Okay. Then each visual primitive, they can have, based on the k-nearest neighbor, they can form small clusters, and those we usually call them a transaction. Okay. For example, you may find these three visual primitives can form a transaction like CBA as a transaction. Okay. Then an image may have many transactions, okay, in every image. Then if there are many images, you may, based on their transactions, you do the frequent pattern mining, you will be able to find some visual patterns. For example, in these pictures, you may find a BA and CA actually are quite frequent together in those transactions. So you can say BA and CA or CBA are frequent patterns, are the frequent visual patterns in those images. So the simple example could be this. Suppose we have 4 pictures. Each picture you may find certain visual primitives form items. Those items, based on the k-nearest neighbor, they form transactions. Then for this car, you may find the two transactions here, G12 and G13. Okay. Then they contain a set of items. EDABC could be the transactions containing those items. Each item actually is a set of visual primitives from the items. Okay. But if you do frequent pattern mining, you may find among those images, you can get AB as frequent item set, and actually this AB represents something related to the wheels of the car. So that's the reason those frequent pattern mining can help identify certain unique features in different images. So then the interesting thing could be, because images are spatial data, then spatial configuration does matter. Then because sometimes those transactions spatially are very close, they may overlap each other, then they may have overcounting problem. For example, this AB, actually in this image, there's only one such AB pattern. But since based on your feature image, they are clustered together, you get two transactions, you actually count AB twice in this picture. Okay. So there's an overcounting problem. Another problem encountered in this visual pattern discovery is uncertainty problem, because you may have some those wheels can be partially occluded by other objects or mixed with other objects. You may have lots of noise. Okay, some feature you may not be able to detect. Another is visual synonym and polysemy problem. That essentially is sometimes the same feature actually may represent different objects, or one object can be represented by different kinds of feature set. Okay. So we need to revise our frequent pattern discovery algorithm to handle this overcounting problem, uncertainty problem, synonym, and polysemy problems. Actually, there are interesting studies in computer vision community. They develop some interesting visual pattern discovery methods for images and video data. So if you are interested in this, I would recommend you study those research papers to gain your knowledge to certain depths. In this session, we are going to discuss another important issue, pattern mining and society. Especially, we'll be focusing on the privacy issue in data mining. We know we are living in a data-rich or big data society. This, of course, creates great opportunity for successful data mining. But on the other hand, people do have concerns whether pattern mining may violate people's privacy or security. Okay. Actually, data mining may naturally have potential adverse side effect is compromise the privacy. Privacy and accuracy are typically contradictory in nature. That means if you want your pattern mining very accurate, in many cases the privacy may be compromised. But if you want to protect your privacy in a very tight manner, then the accuracy of the pattern mining may suffer. Okay. So the problem is we need a new technology to do privacy-preserving data mining. We ensure the data mining will achieve good results, but in the meantime, we're going to protect people's privacy. There are lots of research working on this issue. We call privacy-preserving data mining. Okay. The study generally focused on three categories on privacy. Okay. One we call input privacy, or you can think about data privacy. Essentially, how do we hide data? We can distort data, we can hide data to prevent data miners from reliably extracting confidential or private information. Another category of privacy is output privacy, or we say knowledge privacy, knowledge hiding problem. That means whether even the input data may be okay, but once we find patterns, certain pattern or knowledge could be sensitive. You may not want to disclose it. So how we can guarantee we do the mining, we can ensure the output privacy. Okay. This is another interesting issue. The third issue people studied called owner privacy. That means the people, any party may hold certain data. For example, different hospitals may hold different kinds of patient information. You may want to study, for example, AIDS or heart problems or lung cancer, all those problems. Okay, but you may not want to see where the data come from. That means you actually want to hide the data owners or the hospitals, hide the source of the data. Then you can do more, study. This we call owner privacy problem. So in this short session, we are going to focus on how to ensure input privacy, or you can say data privacy problem. Okay. Of course, one simple approach could be you trust service provider. They are going to anonymize their data, and especially the user private information. They are going to anonymize them, and they are going to ship those anonymized data to data miners. This model we call business-to-business environment or service provider to data miner environment. That means you have to trust both parties. But the problem is, do you really trust them? And most people may say no. Okay, so that's the one. Of course, this could be quite popular in the regular practice, but you want more. Okay, so the second approach we call data anonymization or perturbation. That means we ensure data privacy at owner side, at data source side. Usually this anonymization, even you may not trust the service providers, you actually will try to ask the third-party vendor to anonymize the data before they can release to anybody. Okay, this one we call business to customer environment. And the typical method developed like a data perturbation, data transformation, data hiding. That means we may want to hide some sensitive value or sensitive attributes. Okay. Let's look at this table. This is suppose we have a hospital. It contains certain problem of the data is patient ID. You get zip code, you get age, you get say disease. Okay. People may not be comfortable on this kind of data because even you anonymize patient name, but you may got some people may know the patient's age and zip code. They can easily say, oh, this person got a heart problem. Okay. So then the method could be, what about we make it a little more generalized. We hide the last two digits of zip code. Then we hide the last digit of their age. That means you only know is at a 018 something zip code, and in the 40s got a heart problem. But then you see for the same zip code and same 40s, they got lots of other disease. So you will have no way to tell this person whether they got a heart problem, cancer, flu, or anything else. Okay. So in that sense, you may feel more comfortable. If you got 3 records, you may still not feel very comfortable. But what about you get 100? You probably say that's okay. Okay. So this actually we call the K-anonymity problem. That means every equivalent class, that means they have the same zip code and age, they at least have case records. And if this K is reasonably large, you feel probably much more comfortable because within this 100 different disease, nobody can guess what you have. Okay, so but this may not still be sufficient. For example, what about all these age, the zip code, and in the 30s, everybody got a diabetes. Then then you release it, then easily they can see you do get diabetes. Okay, so that means this record, even this K, is not sufficient. You want to ensure this disease, this sensitive attribute, got at least L distinct values. So we call this is L diversity. But even this L diversity, what about the majority of people got diabetes? You still feel not comfortable. Okay. So there are other studies, further studies, for example, T-closeness, differentiate privacy. So there are lots of research ongoing to see how to ensure people have no way to guess what you have. Okay. Of course, even for error diversity, if the majority, suppose, is HIV negative, probably this majority you will not really have concern because HIV negative is not a concern. Okay, so that's the thing you probably can see. That there are many issues to study to ensure privacy in this way. Okay, so I will not get into detail, but there are many good research papers. I list at the end some typical papers. You may like to go deeper by reading them. Now I'm going to discuss a little on data perturbation methods for privacy preserving pattern mining. Okay. Data perturbation, usually people use a statistic approach. That means using some randomization algorithms to distort the data. One way you can do is we call independent attribute perturbation. That means you take each attribute, you perturb their values independent of the other attributes. Okay? You don't have to think about the other attribute existing. Like you perturb the zip code or you perturb the age, so it doesn't matter. Okay? But for pattern mining, you want to find the correlations. So sometimes you may like to see dependent attribute perturbation because pure independent you do perturb, these correlation may be lost. That means if you want to take care of the correlation across attributes, you may concern to develop some dependent attribute perturbation method. Okay. And for this data perturbation, there are some interesting studies. One method called MASK. That method was if you think your shopping transaction contains lots of items, okay, usually one transaction may only, that means one shopping basket may only contain 10 or 15 items. But if you go to Walmart, there are so many items, you can think all these items is a very long vector. Okay. In your own shopping basket, only a small number of these vectors turns to 1. Okay. But you want to hide what exactly you are buying. Okay. So in that sense, you may turn the other items from 0 to 1, and some of your one item turn to 1 to 0 with certain probability. Okay. With this, if you carefully tuning this P, you may achieve both good average privacy because you insert a lot of randomly picked up item, they will not figure out what you bought, but you still get a good accuracy. The reason is, in general, those patterns, once you randomize a lot of different items, with this randomization, unlikely they will become frequent. Okay, so the pattern may still, your real frequent pattern may show up. Okay, but this method actually may turn, because the majority things are zeros, you may turn many things into 1 with certain probability, so that may increase your number of items in each transaction quite a lot, make your database really big. Okay. Even you can find patterns, it could be substantially slow. There are studies on how to ensure both efficiency and accuracy. Okay. Another method studied called cut and paste operator. This essentially is using uniform randomization. The method is you get a real transaction, you don't increase items in this real transaction, but you take the existing item, you have a probability to randomly replace some existing item with a new item, okay, not present in your original transaction. So as long as you do not make your probability too big to replace them, you still get a good patterns show up. Okay. So, but sometimes if you replace too much, you get a quite worse case, on the accuracy, or you replace too little, you may get a worst case privacy. So there are methods studied how to balance both, how to select items in an organized way, okay, to improve the worst case privacy, but still keep good accuracy. Actually, the experiments show if you want to mine, short transactions, short patterns, short item sets, okay, so these cut and paste randomize the database, you mine it, you may correctly identify 80 to 90% short patterns. like length less or equal to 3. Okay. But if you want to mine long patterns, because of such perturbation, a lot of a long pattern may be destroyed. Okay. So how to effectively mine such long patterns, still remain good privacy, is an open problem. Okay. So privacy-preserving data mining is still a very active research field. There are lots of research papers published. For example, Rakesh Agrawal, they got the first paper published in the year 2000 in Sigmod, and there are books. And I also intentionally put a privacy, differential privacy, like T-closeness, error diversity, those papers here, because I did not really lecture this to any detail. Okay. So interested reader, you may like to read those if you're interested in, further push forward the frontier of privacy preserving in data mining. Thank you. Now we come down to the very last session of this lecture, which is also the very last session of this short course. Looking forward. We have studied a lot of pattern discovery methods, some advanced concepts, some algorithms, and lots of applications. We probably see there are lots of interesting issues to be studied. From the first paper in this field, like 1993, up to now, year 2015, we introduced various kinds of research discoveries and methods, even last until today. Okay. So this is still interesting research and application domain in data mining. So what we want to emphasize is how we further build up new applications using invisible pattern mining approach. What is invisible pattern mining? Is you build these pattern mining methods into various kinds of functions, okay, like a search function, ranking function, recommendation, or other mining functions. Sometimes when people search the web, they may not know they implicitly are using pattern mining results. For example, we have seen we are studying classification. There are so many classification methods, but definitely frequent and discriminated pattern mining could be an interesting contribution to the different repositories of the methods on classification. Then we also studied like graph indexing and the similarity search. When you do indexing, you do search, you do various kinds of retrieval, you may use index constructed by pattern analysis. Then even for pattern mining, we may first mine frequent patterns and doing topic modeling. Then we can get lots of interesting primitives and features for effective text mining. When people are doing software analysis, you may use pattern mining method to discuss lots of bugs or software specification regularities and patterns, which may help us to find bugs in software. For spatial, temporal, trajectory, or movement pattern mining, you may see the frequent pattern analysis can be an interesting method added to this set of weapons. Then for image mining, multimedia data mining, like a video, audio analysis, the pattern analysis could be an implicit approach, methods built inside. Even for biological and chemical data analysis, like analyze DNA sequences or biological graphs, lots of pattern mining may be used as primitives. Even in clustering, for example, we are going to study clustering in data mining. In this course, I'm going to introduce you subspace clustering, which actually frequent pattern mining will become another interesting technique for subspace clustering. Okay. Even people search the web or make a recommendation of your products or study click streams to enhance your search, the pattern mining may play an important role in this. So people can see pattern mining can be applied in many different domains. So this invisible pattern mining could be very important, taking this as a pre-processing as some component in your whole analysis package. So we are facing very big data, we are facing lots of challenges, but pattern mining surely is a tool. So I hope by learning this course, you will become part of research and development force to push pattern mining into new era on both research and applications. Hopefully, in the future, in your work, you may find, using the material you learned from this course, you are going to develop some interesting functions and push the technology into application, into the new frontier. Thank you.